In this lecture, we will discuss an example of a logistic regression. So consider a process of admission into a university. Now this is a binary process. Either you are successful in getting an admission, it's 1, or you are a failure in getting an admission, this is 0. So the outcome is 1 or 0, success or failure. Now there are 3 predictors: SAT scores, GPA, and race or ethnicity. And this is the admission statistics. So for student 1, so this is the data you have. For student 1, he was admitted. His SAT score was 1320, GPA was 3.64, his race was 3. So the race we are putting as categorical values 1, 2, 3 or 4. So the race could be anything out of these 4. So consider another student 2. The student was also admitted. He had a SAT score of 1600, his GPA was 3.97 and his race was 1. And say this is student 3. His SAT score was 1210, GPA was 3.1, his race was 4, and he was not admitted. So you have this data. Given such a data, we want to have a model which can predict odds ratio for an applicant given the predictors. So these are the predictors, that is SAT, GPA and race. So given his SAT scores, his GPA and his race. So say you are admissions counselor, a student comes to you and he says that, say this university is U1. So this data is for university U1. So he gives you his SAT score, his GPA and his race, and he asks you, what is the probability of my success in getting into this university U1? So if you have a model for predicting odds ratio, you can give him exactly what are his chances, and then he can decide how he wants to spend the application money. So again, SAT scores and GPA, these are continuous variables, and this race is a categorical data. So the race can take only 4 values, 1, 2, 3, 4. And SAT and GPA are continuous. So SAT could be a continuous variable, GPA could be continuous variable. So let us now see the R commands. So this first command, rm list, this is nothing but to clear the memory. So it is always a good option to clear memory before you start, because then there is no confusion while running the program. So you clear the memory. So first you read the data. So this is the address of the file. So this is where the file is stored. This is the name of the file. So this is the file name. And this part is the address. Header is true because we have given the header in the data. So head data 1, 2, it just displays the first 2 rows of the data set. So the first row is 0, 760, 3.56, race is 3. Second is admitted 1320, 3.64, race is 3. So again, the race in the entire data set could be from 1, 2, 3 or 4. So the first thing is we have to deal with the categorical data. This race takes on value 1, 2, 3, 4. So we have to tell R that you need to treat this specifically, because these 2 are continuous and these are exactly how you would put them in a linear model, but this has to be taken care of. So you put data 1 race. So this data 1 race is this column. So we are telling the R focus on data 1 race and then factor it out. Factor out this column data 1 race. So again, data 1 is the name of this table and race is the name of the column. So R will make a factor out of it. So now you have the model, my logit, this is GLM. So notice this is not LM but GLM. So admit, so this admit as a function of SAT, GPA, race. So SAT, GPA, race, these are the 3 predictors. And we want to make a prediction about this variable admit. That's why you have admit. So you have admit SAT, GPA and race. So data is data 1, this data which we have read. The family is binomial. So this will make a model. So the model is now MyLogit. So once you have the model, now you want to estimate the probabilities. So now you want to find out what are the probabilities. So here we are going to compute the probability. So we are going to feed in three things. We will feed in SAT score, GPA and race. So these are the three predictors we need: SAT, GPA and race, and that's what we feed in: SAT, GPA and race. So SAT we are feeding in as 1600, GPA 4, race we are feeding in as 1. So notice that I am feeding in as factor 1. So now you predict it, you predict your model. Your model name is MyLogit right here. MyLogit. New data is the data for which you find the probability. So this is the new data, and type is response. So this is the response variable. So admission is a response variable. So when you type this in, you get the probability is 0.714417 for admission. So this 1 corresponds to admit. So R will always spit out 1 and then corresponding probability of admission. So this person who has a SAT score of 1600, his GPA is 4 and his race is 1, his probability of getting admitted is 0.71. So now we will keep changing this and you will keep finding new and new probability. So the idea of the model is precisely this: someone comes with you a SAT score, a GPA and a race. Given this data, you can tell them what is your probability of admission. Now you plug in new data, you keep the SAT scores the same, GPA the same, just change the race and then do prediction again. Now you get probability as 0.59822. This is the probability of admission. So again there will be 1 here. This 1 corresponds to admission. Now you can compute probabilities like this by keep on feeding in SAT scores, GPA and race. But what you want to find out is whether this 0.598 is different from the previously computed probability of 0.7. So how do we do that? For that we have to interpret the coefficients of our model. So notice that in a linear model, if 0 lies in the confidence interval, so if 0 lies in the confidence interval, then the corresponding coefficient is not significant, because that corresponding coefficient, which is say alpha, which is equal to 0 statistically. So here we are using exponents for odds ratio. So if you take exponent of 0, that is 1. So in this case the confidence interval should not contain 1. So let us see this now. So this is the command. You have the coefficients of your model, which is MyLogit, and confidence interval of the model, which is again MyLogit. You run this, this is what you will get. So first you figure out which interval has 1 in it. So intercept is not important, so this you forget anyway. So you start with SAT. This interval does not contain 1, so this you can choose as a impacting factor. GPA, this interval again does not contain 1, so this is a impacting factor. Race 2, this interval contains 1, so this is not an impacting factor. Race 3, this interval does not contain 1. Notice that this goes from 0.33 to 1.06. That's why there is a 1 here. This interval does not contain 1. This is fine. This interval does not contain 1. This is fine. Now let us start interpreting these coefficients one by one. So as I said before, intercept is a constant. You can't do anything about it, so forget about this. So this you forget. You start with SAT. So SAT is 1.001. Now this is very small for interpretation because it's very close to 1. So we will come to this later, but this is statistically significant as you see here. So we have to come to this later. Let us start with bigger numbers and smaller numbers which give us direct interpretation. So you do GPA first. So GPA is 2.29. That means 1 unit increase in GPA, 1 unit increase in GPA will increase your odds by, will increase your odds ratio by 2.29. So if your GPA goes 1 unit higher, then your odds go high. They go to 2.29. So that is the interpretation. And the best way to do it is, say you put 2 here and then you put 3 and see how the probability changes. And the change in probability would be significant because this model tells us that the change in GPA is significant. Now change in race 2 is not significant. So again, for race, the base case is always race 1. So notice that race 1 is not even here. So our base case is race 1. So this model shows us this race 2 is not important. So first thing is that any probability you get by changing to race 2 is not different from race 1. But race 2, this is not different, but race 3 and race 4 are different. So race 3 and race 4 are different. So what does this 0.3 mean? So odds ratio now is less than 1. So notice that odds ratio is less than 1 because it is 0.3. And we are at race 3 now. So this means, say if you change your race here from 2 to 3, then there will be some probability which will come out. Whatever probability will come out will be significantly different. And that this odds ratio less than 1 means that if the race is changed from 1 to 3, then the odds of admission are against you. The odds of admission are against you for this particular university U1. So maybe you should look for another university in which the odds are in favor of you. Similarly for race 4, the odds are 0.23. So 0.23 again is less than 1. So race 4, again the base case is race 1. So if your race changes from 1 to 4, you will expect your probability to decrease, and the decrease would be statistically significant because this interval does not contain 1. So this again is against you. So U1 university is against you. So only people with race 1 and race 2 have no impact upon their probability of admission. Race 3 and race 4, if you calculate any probability, that would be statistically different. So this is how you interpret this table and this model. So the best thing is to keep on changing your new data here and keep on predicting probabilities. And then you have to say why your probability is statistically different. Your probability is statistically different precisely because your confidence interval says so. So the only thing you should change is, you should change the SAT score, which will give you different things. You should change the GPA, and the race should only be changed to 3, 4. 1 and 2, change between 1 and 2 does not produce any statistically significant results. So the last thing is we want to interpret is the SAT scores. As I said, the SAT scores are pretty close to 1 and therefore they are difficult to interpret. So the way you interpret it is, what you do is you take log of this value. So we are going to take log of this value. So you put 1 by alpha is equal to 1 by log of this value, which is 1.00109. So this will come out to be 917.9311. And this is important. So whenever you're close to 1, you first do this. You compute 1 over log of the estimate because we are getting back to the coefficient. And the thumb rule is, so if you change your coefficient by plus minus 1 by alpha, the corresponding change in probability by 0.5 plus minus 0.23. So this change is constant. So if you change by plus minus 1 over alpha, that is 1 over log of this, your probability will change by this. So what does this mean? So if you change your SAT score, so you're given your SAT score, if you decrease from your SAT score this much amount, so this is approximately equal to 918. So from your SAT score, if you take out 918, then your probability will go from 0.5 to 0.5 minus 0.23. If you increase your SAT score by 918, then your probability, if it was 0.5, it will go up to 0.5 plus 0.23. So notice that this 918 is a huge number. So to make sense of SAT scores, what you need to do is, we had SAT scores like this, 1600 and so on, 1600, 1400, 1320. So this huge number tells you that the best way to deal with SAT scores is probably divide all of the SAT scores by 1000, 1.6, 1.4, 1.32, and then run your logit model again to get some significant results, because this is clearly significant, but it is 1, so it is not showing you much change, because change in 1 unit by SAT score doesn't seem to improve your chances of admission by much. But if you change by 918, then definitely your probabilities are changing dramatically. So you want to scale it appropriately. So this means that your model is not scaled properly. So maybe divide your SAT scores by 1000 and run it again. But again, you don't have to do this. You just have to see that this is a significant parameter, because there is no 1 in the interval. So if you change the SAT scores, any change in probability you get is significant. So the last thing is, you can change SAT scores, get significant probability. You can change GPA, you get significant probability. You can change race 3, race 4. Only thing you cannot do much is change between 1 and 2. And again, for the races, the base case is always 1.